Okay, guys, we're going to go ahead and get started. So we're going to continue talking about domain and continuity today. This time we're going to look at another type of function. So last time we talked about polynomials, we talked about exponential functions, square root functions, and what was the last one? Logs. So today we're going to talk about another type of function. We're going to focus on rational functions today and into tomorrow. So a rational function is defined as a function that is the ratio of two polynomials. It looks like a fraction where the top and the bottom are both polynomials. So polynomials, remember, are variables that have integer exponents, usually positive integer exponents. So they look like these guys: x minus 5 over x squared plus 2x, or x to the fourth minus 16 over x squared plus 3x minus 4, or even just 5 over 3x. Probably the simplest rational function, if we wanted to talk about a parent rational function, would be just 1 over x. Okay, but the idea is I've got some variables in the bottom of a fraction. So rational functions, these are rational functions. Because we're looking at variables in the bottom of a function, we need to be concerned with this function being undefined, okay? With when is the bottom 0. So if my parent function, if that's what I'm looking at, if I let x be 0, then that means I would have 1 over 0, and that is undefined. And so I can't have that. I cannot let x be 0. So yesterday with our square root functions and our log functions, we were talking about places that caused us problems, right? So if I'm looking at a square root function, if I take the square root of a negative, that's an issue. Those are non-real values. With our, let me flip back for just a second. With our log functions, we talked about how the argument cannot be 0 and cannot be a negative number. So we had to restrict our domain because of that. And again, same idea with our square root functions. We didn't want to be taking the square root of a negative number, so we had to restrict our domain based on that. So we're going to see something similar with rational functions today. I want to start with the rational functions that we see on page 11. And I just want to start with which values of x would make our function undefined. So what are the values of x? Let's start there, that are no-goes. We cannot have this value of x. So if I look at a, there is a value that if I used it for x, if I plugged it in for x, would give me an undefined function. What's the value of x that I cannot use? 2. If x equals 2, my function is undefined. Anything else is okay, but if I use 2 for x, that means the bottom would be 0. So x cannot be 2. My domain then would be anything but 2, all real numbers but 2. In interval notation, that would look like negative infinity to 2. Notice it's a parenthesis, not a bracket, because we cannot include 2. And then 2 to infinity. What about b? Where would I have problems with b? What values for x?
If x was 1 or negative 3?
Yeah, I can't be negative 3. Because if I plug negative 3 into this factor on the bottom, that would be 0. And then 0 times anything is 0. And the bottom would be 0. X can also not be positive 1. When I set up my domain then, I can have negative infinity up to negative 3. And then negative 3 to positive 1. And then 1 to infinity. I have to exclude negative 3 and 1 from the domain. Can't have them. Weird stuff happens. We'll talk about what weird stuff happens in a little bit. But for right now, I just want us to recognize I can't have them. They'd make the denominator 0. What about C? What values can I not have? What are you looking for specifically before you answer? How are you coming up with your answers? Yeah, go ahead.
So when I kind of like look at it, I look at each like individual like thinking the parentheses,
Mhm.
I think like what number will make that equal to 0?
Mhm.
And then if you multiply by each other, it's just gonna be 0.
Exactly. So you were about to tell me?
One of them is -4.
One of them is -4, cannot be -4. The other one's a little bit trickier because it's 3x minus 4. 4/3. X cannot be 4/3. Okay. You can, we're talking about what value would make this factor 0. You can, if you would like, set up a little equation to solve to find those X values. So if for whatever reason the brain's a little fuzzy, how are they getting -4? You can set your factors on the bottom equal to 0 and solve. Particularly when you have a coefficient for X and it's just maybe a little bit trickier, you can solve to get those values. And then when I set up my domain, be careful. Remember, I will go from -infinity to -4 is what I'll hit first. So don't tell me from -infinity to 4/3 and then from 4/3 to -4, because when you go from -infinity to 4/3, you've included -4 in that and you don't want to. So you do have to go in order for your domain. So this would be -infinity to -4, and then -4 to 4/3, and then 4/3 to infinity. Last one, what can X not be? X cannot be 0. Yep. 0 squared would still be 0. So this would be -infinity to 0, and then 0 to infinity. So when we're looking at the domain of a rational function, what we need to really be concerned with are values of X that makes a function undefined. So really quickly, I want to review the types of discontinuities that we talked about earlier this week. So on the next page, here we go. Exact same pictures we saw earlier in this unit, okay? This guy right here where I have a single point that is not defined anywhere. Otherwise, the rest of my function acts as I expect, except for that one spot. That's what we call a hole or a removable discontinuity. When I have this sort of vertical split here, that is what we call a vertical asymptote. And then when I have a vertical distance between maybe one part of a function and another part of a function, we'll see this a lot with piecewise functions. This is what we call a jump discontinuity. So I want to start our next problem. We're going to start talking about how I can differentiate what type of discontinuity I have in a rational function. So I want to start our next problem by first finding those values I need to exclude from the domain. So our function that we have here has a denominator that is not in factored form. Everything else I've given you so far has been in factored form. We're going to start to see functions that are not in factored form. For some of you, factoring was last year. For some of you, factoring was 2 years ago. So we'll have some time to review and practice. If that is, we get to these problems and you're like, oh man, I don't feel like super great about that. We'll have some time to review and practice those skills. And for this lesson, I'm not going to give you anything that's like really wild because that's not our biggest focus. But I just want you to be aware we're going to see some factoring. So what I have here is a trinomial. My lead coefficient is just 1. So I'm going to look for factors of C that would add to B. So what would multiply to -12 but add to -1? I'm going to want to use -4 and 3. So my factored form here would be x minus 4 times x plus 3. So what values do I need to exclude from the domain? What values can I not have in the domain? I cannot use these for x. Go ahead. -3 and +4. This is the graph of that function. Okay, this is the graph of that function. So we said we had excluded values at -3 and at 4. I cannot include -3 or 4 in the domain. So when x is -3 and when x is 4, I can see some of these discontinuities on my graph. When x is -3, what do we have? A hole. When x is 4, what do we have? A vertical asymptote. Good. On the next page, I've got another set of examples for you here. There is one typo in your notes. This should be x plus 1. For that first one should be x plus 1 on the bottom. So if I look at my excluded value for this first function, I need to exclude -1 from the domain. And then what do you see on the graph when x is -1? An asymptote, right? A vertical asymptote. For our second example here, we would need to exclude 2 and -1. X can't be either of those. When x is -1, we see a vertical asymptote again. What about when x is 2? What do you see? A hole. This pattern is going to be true for all rational functions. When you have a excluded value that results from a factor you could reduce, a reducible factor. So for example, if I gave you this and asked you to simplify x minus 2 as a factor on top and on bottom, you could reduce that factor. If it's a reducible factor, it's a removable discontinuity. If it's reducible, it's removable. So factors, or I should say excluded values that come from factors you can reduce are going to result in a hole. Excluded values that come from factors, there we go. Excluded values that come from factors you cannot reduce are going to give you a vertical asymptote. Okay, so non-reducible factors are going to give you a vertical asymptote. Reducible factors are going to give you a hole. If I've got the graph, I can look at the graph and see there's a hole there, there's an asymptote here. If I don't have the graph, then we can still use that function to be able to classify what those discontinuities will be. So we can state the domain. We know we need to exclude those values that make our function undefined. And we can also classify those values that we're excluding as holes or vertical asymptotes. Those are the discontinuities that we'll see in a rational function. Okay. So for our first, or I guess these are the examples that we saw in our first example. These were the functions. So we already talked about their excluded values. Let's now classify them. So for A, we said x cannot be 2. When x is 2, is that a hole or an asymptote? So is this a reducible factor? No. You cannot reduce just the x. We can only reduce factors, right? Like if I had, and I'm glad you said that because somebody else would do that same thing. So if I had, let's use numbers instead of variables. If I had 5 plus 6 over 5 plus 1, can I just reduce the 5s? Is that going to give you the same? Absolutely not, right? Because this should be 11 over 6. If I reduce the 5s, I get 6 over 1. Are those the same? No. So thank you. We cannot reduce the x's. I have to be able to reduce the entire factor. Okay, I can reduce factors. I cannot reduce if I see something that has a like plus or minus sign attached to it. So I cannot reduce this factor. That means that that excluded value must be a vertical asymptote. For vertical asymptotes, we do need to write the whole equation. When I describe an asymptote, I'm describing a line. So I need to give the equation of a line. It's the line x equals 2. That is a vertical asymptote. For B, we said we need to exclude -3 and we need to exclude 1. Can I reduce either of those factors? Nope. So what do I know about those places? They're both asymptotes. X equals -3 is a vertical asymptote, and x equals 1 is a vertical asymptote. For C, we said we need to exclude 4/3, and we need to exclude -4. I can't see if either of these factors reduce because the top of our function is not in factored form. So I've got to factor the top. My lead coefficient is 1 on my trinomial again. So factors of C that add to B, factors of 12 that add to 8. That would be 2 and 6. So this would be x plus 2 times x plus 6. Can I reduce either of my factors on the bottom? No. So what do I know about 4/3 and 4? -4? They're both vertical asymptotes. For D, we said we need to exclude 0. On the top, we have a GCF here. I can factor out an x. That would leave me with -x² plus 25. When we do more factoring work, I would factor out that negative sign as well, but I don't really care about the sign for looking at my excluded values. So could I do any reducing here? I sure could. X² is x times x. So I could reduce an x. I also still have an x on the bottom though. So at 0, I have reason to think that I would see a hole. I also have reason to think I would see a vertical asymptote. Anytime that you see a situation like this where at one specific value you have both things happening, the vertical asymptote is going to win. So at x equals 0, we would have a vertical asymptote. Even though I could reduce one of those x's, the asymptote is going to overpower the whole. Last few problems for today. We've got some problems where we're going to need to factor on the next page with example 2. So we're going to work through some of this factoring together. I want you to notice we've got a lot of trinomials here. Sometimes the lead coefficient is 1, like what we've seen before. Sometimes it's something greater than 1. We've got difference of squares. We've got stuff that has common factors, GCFs. So we're going to do a little quick practice together of all of this, just sort of as a review. Let me see where we're at on time. Okay, yeah, we got plenty of time. Okay, so let's start with A. We have a trinomial here, but the lead coefficient is not 1. Okay. Depending on who your teacher was when you learned how to factor, you may have seen a lot of different methods. My personal preference for something like this is to use a C method. If that is not your personal preference, that is okay. Some people will set up their factors and say, well, it's got to be 2x and then the other one x, and I'll just sort of guess and check factors of 9 to figure out what goes here. If that is how you factor when your lead coefficient is not 1, go for it. If you need a little bit more process and structure, I prefer AC method. There's slide method. I'm sure there's other ones too that I haven't taught, but I want you to do whatever makes sense to you. If you're an AC method person, it would be A times C, and then factors of this that add to negative 19. That would be negative 1 times negative 18. And then we don't hop directly into our factors with AC method. We rewrite that middle using the factors that we've got. And once I'm in 4 terms, we can use grouping to factor here. And then I look for a GCF for each group. In my first group, the GCF is X. That would leave me with 2X minus 1. The greatest common factor for my second group would be negative 9. That leaves me with 2X minus 1. Be careful, since I took out a negative as part of my GCF, the signs change here. Your bit in parentheses should always be the same for AC method. And now this is your GCF. This is your common factor for this. And left over, you would have X minus 9. So the bottom here would be 2X minus 1 times X minus 9. From here, I can see my excluded values. So I would need to exclude 1/2, and I would need to exclude 9. Will 1/2 be an asymptote or a whole? Asymptote. I cannot reduce this factor with what's on top, so that's a vertical asymptote. How about 9? Asymptote or whole there? Also an asymptote. I cannot reduce this factor, so that is an asymptote. And then my directions ask me to give the domain. So my domain here would be negative infinity to 1/2, then 1/2 to 9, then 9 to infinity. We'll skip E right now since we've already factored some trinomials like this, just so that we can hit some stuff we haven't seen yet. I'm going to go down to C. I do need, when I'm looking at classifying those excluded values, I do need to make sure I have factored form on top and bottom. On top, this is a trinomial, lead coefficient of 1, so factors of C that add to B, factors of negative 40 that add to 3, that'd be 8 and negative 5. So this is X plus 8 times X minus 5. This is just so I can classify the excluded values I see on the bottom. I need to know if those factors reduce or not. On the bottom, trinomial, my lead coefficient is not 1, but I do see that I have a GCF of 5 here. So my first step is going to be to factor out 5 from every term. Then I will factor what's left. So this is a trinomial whose lead coefficient is 1, factors of negative 2 that add to 1, that would be 2 and 1. So this would be X plus 2 times X minus 1, 2 and negative 1, I should say. So our factored form for this would be 5 times X plus 2 times X minus 1. My excluded values then would be negative 2 and positive 1. Classify them for me. Negative 2 is a asymptote. I cannot reduce that factor, so it's a vertical asymptote. How about positive 1, asymptote or whole? Asymptote or whole? Can I reduce this factor with anything on the top? No. So that means it's an asymptote. My domain then would be negative infinity to negative 2, negative 2 to 1, and 1 to infinity. For D, I've got some factoring that I can do on the bottom. This is a difference of squares, called so because it's a difference, it's subtraction of two perfect squares. X squared came from X that I squared, and 49 came from 7 squared. So my factored form here would be X plus 7 times X minus 7. What values do I need to exclude here? What can X not be? 7 and negative 7. X cannot be 7. X cannot be negative 7. Can I reduce either of those factors with what's on the top? Nope. So they are vertical asymptotes. For E, oh, I forgot to write the domain here. So our domain would be negative infinity to negative 7, negative 7 to 7, and 7 to infinity. For E, I have x squared plus 3 on the bottom. This is not factorable over the real numbers. It's a sum, right? It's got sort of a similar format to our difference of squares with this sort of binomial structure, but it's a sum instead of a difference. And 3 is not a perfect square. So this is not something we can factor with real numbers. So we're not going to factor except with real numbers for today. This is not something we can factor. Are there values I need to exclude from the domain? What would I need to exclude here? Is there anything that I can square? And so let's pretend this was just x for a second. If it were just x, what would we need to exclude? Negative 3. But since it's squared, what happens if I plug in negative 3? I get a positive, right? So I need something negative here. I need something that if I square it would give me negative 3. Is there anything I can square to get negative 3? No, no real numbers squared give me something negative. So do I need to exclude anything from the domain here? No, my domain on this one is all real numbers. We'll see and we'll focus on rational functions that have asymptotes, that have holes, that have these discontinuities. But we can also have rational functions that don't have any of those things. They don't have vertical asymptotes, they don't have holes. And that's what we're seeing here. It's a rational function whose domain is all real numbers. We're defined everywhere. And then F. If I factor the bottom, I have a GCF of X. I'm going to start by pulling out my GCF of X. When I do that, I no longer have X squared. I'm down to just what we call linear factors, X to the power of 1. So I don't have anything else I need to do to factor here. What are the values that I need to exclude? There, anything X cannot be, or it would make my function undefined. X cannot be 0. If I plug in 0 here, then the whole bottom would be 0. And then there's one more. What else can X not be? Negative 5. X cannot be negative 5. So I know my domain would be negative infinity to negative 5, and then negative 5 to 0, and then 0 to infinity. Right? Splitting my domain up everywhere that I have one of those excluded values. In order to classify these, we have to factor the top as well to see if any of these will reduce. So on top, I have a trinomial. Lead coefficient is 1. So this would be factors of negative 10 that add to 3. That would be 5 times negative 2. So I have x plus 5 times x minus 2. Can I reduce anything? What can I reduce? The x plus 5, right? So that means at negative 5, what do I have? A whole. And at 0, what do I have? A vertical asymptote. For tonight, I have a Delta Math assignment for you that is a review of factoring. Tomorrow, we're going to see some functions that have a little bit, maybe more intense factoring or a little bit heavier reliance on factoring.